Dear colleagues, allow me to present our joint research with my colleagues from the Institute of Mechanical Engineering Problems of the National Academy of Science of Ukraine. The topic of my talk is a regular layout problem for additive production. The layout problems have a wide spectrum of applications, including space engineering, nanotechnologies, logistics, biology, medicine, material science, just to name a few. And one of the most interesting applications is additive manufacturing or 3D printing. To minimize the cost of 3D parts production using selective sintering technology, the number of printing layers should be minimized. This problem can be formulated as a layout problem of 3D parts in the working chamber of a 3D printing to minimize the height of the occupied part of the chamber. We study here the layout problem in the following formulation. As the models of 3D parts, convex or non-convex polyhedra are considered. Our objects can be continuously rotated and translated, and the model of the container or printing chamber is designed as cuboid of variable dimensions. Each object has to be arranged fully inside the container. In addition, the minimum allowable distance between each pair of 3D objects is defined regarding 3D printing standards. The objective is to place the given collection of objects inside the container to minimize the height of the container, taking into account the distance constraints. The mathematical mode of the problem is a part of computational geometry. For analytical description of the placement constraints, we employ the Phi-function technique. By definition, a function depends on placement parameters of two objects. It is continuous and everywhere defined, and the value of the function is greater than 0 if objects do not overlap, is equal to 0 if objects touch, and less than 0 if objects have common interior points. And non-negative values of the function provide the objects non-overlapping. For more complicated shapes of 3D parts, we use the extension of the Phi-function called a Quasi-Phi-function, and the maximum of this function on auxiliary variables coincide with the Phi-function for these two objects. In order to state distance constraints, we use so-called adjusted Phi-functions and adjusted quasi-Phi-functions. And non-negative values of adjusted Phi-function provide the minimal allowable distances between 3D objects. Based on adjusted quasi-Phi-function for non-overlapping constraints of placement objects and Phi-function for containment constraint for each object and a complement of our container, mathematical model of the layout problem can be presented as a nonlinear programming model where visible region is described in terms of Phi-functions and quasi-Phi-function. Our model is exact formulation of the large-scale layout problem. Therefore, even finding a local optimal solution is a complicated task for available state-of-the-art NLP solvers. In order to search for a good local optimal solution, we propose the following multi-start solution strategy. This strategy involves three main stages. The first, we generate the set of feasible placement parameters of our objects. Then we search for a local minimum for the problem starting from each feasible point found at the previous stage. Finally, we choose the best local minimum as the final solution of our layout problem. To realize the first stage, we developed the first algorithm of generated feasible starting points based on homothetic transformation of objects. For local optimization, we propose special procedure that allows reducing our original large-scale layout problem to a sequence of NLP subproblems of considerably smaller dimensions. The picture provides illustration to the local optimization procedure that corresponds to arrangement of objects with respect to the feasible starting point, to local minimum points of subproblems, and the local optimal solution of the original problem. And now we present some instances to demonstrate the efficiency of our approach. For layout, convex, non-convex objects, with and without allowable distances, some benchmark instances, and also we compare our results with those published before, and we got improvements regarding the value of the objective function and the computational time. The authors are partially supported by the program of the State Priority Scientific Research and Technological Development of the Department of Physical and Technical Problems of Energy of the National Academy of Sciences of Ukraine. Thank you for your attention.